A diesel engine is quite different from a gasoline engine in the way the fuel is ignited. In a diesel engine, only air is drawn into the combustion chambers and compressed. When the fuel is injected into this hot, highly pressurized air, it ignites spontaneously. The diesel engine's power output is controlled by regulating the amount of fuel that is injected into the combustion chambers. In this video, we will study about the distributor type injection pump, often called the VE pump, that is used with diesel engines. We will be using the VE pump that is used in the 1C diesel engine as our model. First, let's review the fuel system in general. The component in the center is the VE pump. The fuel is drawn from the fuel tank into the fuel filter by the feed pump. The filter traps any water and dirt that may be present in the fuel. The fuel is forced forward by the feed pump into the VE pump housing. In this illustration, the color representing the fuel becomes darker as the pressure rises. The fuel reaching the housing is compressed further by the pump plunger and travels through the delivery valve and the injection nozzles before it is injected into the combustion chambers. Part of the fuel reaching each injection nozzle is used to lubricate the nozzle before returning to the fuel tank. Part of the fuel reaching the VE pump housing is used to lubricate the housing. It also cools the pump before it returns to the fuel tank through a tiny hole in the overflow screw. Now we will look at the construction of the VE pump and study the pump functions one by one. This is a real VE pump. We also have a cutaway model of the pump. It was made to reveal the inside of the pump. We'll use the VE pump diagram and the cutaway model to see how each part works. The drive shaft at the left of this illustration is driven by the engine's timing belt via the pulley and operates the VE pump. This is the feed pump, which is driven by the drive shaft. The feed pump forces the fuel into the pump housing. The feed pump is shown rotated 90 degrees to the left to show its design. In reality, the feed pump is fitted here at a right angle with the drive shaft. This is the pump plunger, which distributes the fuel to each nozzle under high pressure. In a sense, the pump plunger is the heart of the VE pump. This is the fuel cutoff solenoid. When the ignition switch is turned off, this solenoid goes off and shuts off the supply of fuel to the engine. This is the governor, whose function is to regulate the amount of fuel injected. The engine speed and power output are altered by the governor in accordance with the amount of fuel injected. This is the timer, which controls the timing of fuel injection. We will now study the function of each component in more detail. We will begin with the feed pump. The feed pump forces the fuel into the pump housing under pressure. As the pump rotates, the four vanes draw fuel from the filter and send it onward under pressure. This pressure, called the delivery pressure, is regulated by the regulating valve and varies in proportion to the engine speed. Let's go on to the pump plunger next. We'll use the cutaway model to show how the pump plunger works. Here, the plunger is moving much more slowly than in reality. Can you see how the plunger rotates while moving back and forth within the cylinder? This is how the plunger distributes the fuel to the various nozzles under pressure. Let's look at the construction of the plunger next. The pump plunger and the cam plate are shown here, removed from the pump unit. As the drive shaft at the left rotates, it drives the cam plate and the pump plunger at the same speed via a coupling. The drive shaft rotates at half the speed of the engine's crankshaft. A roller is fitted to the roller ring. The cam plate is constantly pushed by a plunger spring against the rollers. As the cam plate rotates, the face cams ride on the rollers, pushing the plunger in and out. The cam plate has the same number of face cams as the engine has cylinders. In this case, there are 4 face cams on the cam plate because this engine has 4 cylinders. Notice that the pump plunger and cam plate rotate and reciprocate as a unit. Here, the spring and the cylinders are shown removed to demonstrate the movement of the pump plunger. Remember that the pump plunger completes 4 reciprocating movements while it rotates once. Now, let's see what the plunger achieves by these rotating and reciprocating movements. The pump plunger distributes fuel to the 4 nozzles in sequence as it completes one turn. The reciprocating movement of the plunger is used to draw in fuel and deliver it to the nozzles under pressure. These 2 movements are interlinked with each other so that the fuel is forced into the 4 nozzles sequentially while the plunger completes a turn. Now, let's see what happens during each stroke of the plunger. The first is the fuel suction stroke. One of the suction grooves aligns with the suction port in this stage. There are 4 suction grooves. The suction occurs 4 times while the plunger completes a turn. The fuel is drawn in and forced into the fuel passage that runs through the plunger. As the face cams move off of the rollers, the plunger moves to the left, and the fuel is drawn in from a suction groove and then forced into the pressure chamber and the passage hole in the plunger. Now, let's review the suction stroke using the cutaway model. The next is the delivery stroke. As the pump plunger rotates further, the suction port is closed off and the distribution port becomes open to the distribution passage. As the plunger rotates further, the face cams ride up on the rollers, moving the plunger to the right. Pressure builds up inside the plunger, but since there is only one exit from the plunger, the pressurized fuel travels through the distribution passage, pushes open the delivery valve, and flows into the nozzle. Let's see this using the cutaway model. The nozzle opens when the pressure rises to 120 kilograms per centimeter squared, and the fuel is injected into the combustion chamber. A total of 4 distribution passages are located around the plunger cylinder, 90 degrees apart from each other. The fuel is forced into 4 nozzles sequentially from these passages. We will now go to the termination stroke. As the plunger keeps moving to the right, the 2 spill ports are uncovered by the spill ring. This causes the pressurized fuel remaining in the plunger to be forced back inside the pump housing, releasing the pressure and ending fuel injection. The distance the pump plunger moves from the start of fuel delivery to the end of fuel injection is called the effective stroke. Fuel is sent to and injected from the nozzles in an amount proportional to the length of the effective stroke. Now, let's assume that the spill ring is moved to the left by the governor, which we will discuss later. In such a case, the effective stroke decreases and a smaller amount of fuel is injected. If the spill ring is moved to the right, the effective stroke increases and more fuel is injected. In other words, the amount of fuel injected can be regulated by changing the position of the spill ring, which in turn determines the effective stroke. This relationship is shown in the graph. We hope you now have a better understanding of the operation of the pump plunger. Our next subject is the delivery valve. A delivery valve is located inside each distribution passage and is designed to draw back the unused fuel into the pump housing to keep the passage airtight. There are 4 delivery valves, 1 for each of the 4 distribution passages. Let's see how they work. As long as the fuel is pressurized, the distribution passage is kept open by this pressure. When delivery of the fuel is ended, the valve is forced back by the spring. When the valve resumes its seated position, the passage is closed off and the fuel is drawn back in. The pressure in the high pressure line drops quickly to about 20 kilograms per centimeter squared to prevent after dribble from the nozzle. At the same time, when the valve seats itself snugly on the delivery valve seat, it seals off the high pressure line from the pump cylinder. Our next subject of study is the governor. It plays the important role of controlling the amount of fuel injected into the engine. A centrifugal mechanical governor is used in the VE pump, and we will study how it works next. As we saw earlier when we talked about the effective stroke of the plunger, the amount of fuel that is injected is regulated by moving the spill ring to the left or right as needed. This movement of the spill ring is carried out by the governor. The spill ring is provided with a groove, and the lower end of the governor lever assembly is seated in this groove in such a way that the other end of the lever can move freely about the lever's fulcrum. The free-moving end is connected to the accelerator pedal via a spring and is pulled to the left when the pedal is depressed. As a result, the spill ring moves to the right and a larger amount of fuel is injected. At the same time, the governor's sleeve is pushed to the right in proportion to the engine speed. This, in turn, pushes the upper side of the governor lever assembly to the right. In other words, when the engine speed increases above a certain level, the spill ring moves to the left and the amount of fuel injected is reduced accordingly. The spill ring is controlled by two forces, the pulling force A and the pushing force B. The position at which the spill ring stabilizes is determined by the balance of these two forces, and this in turn determines the amount of fuel that is injected. Governors may be classified into the all-speed governor and the minimum-maximum speed governor, depending on their function. Let's study the design of the all-speed governor. It has a guide lever fitted just above the spill ring. A tension lever is fitted to the guide lever in such a way that it can move freely about its fulcrum. Another lever, called the control lever, is fitted over it, and both levers move about the same fulcrum. The lower end of the control lever is seated in the groove of the spill ring and slides the ring in either direction. The flyweights are swung outwards by centrifugal force as the engine speed increases. This causes the governor sleeve to move to the right, pushing the control lever to the right. Now, let's see how an all-speed governor operates. When the engine is started, its speed is still very low, and only a negligible centrifugal force is acting on the flyweights. So the control lever is pulled to the left by the start spring and pushes the governor sleeve to the left. As a result, the spill ring is moved all the way to the right, supplying more than the usual amount of fuel to the engine. Now, let's assume that the engine is idling. As the engine starts and its speed increases, the flyweights swing outwards and push the governor sleeve to the right. This is the idling condition. The control lever compresses both the idling spring and the damper spring and keeps moving to the right until the force applied by the springs balances the centrifugal force. The spill ring moves to the left until the idling position is reached. Now, let's see what happens under full load conditions. When the accelerator pedal is fully depressed, the control spring is stretched to its full length. This pulls the tension lever and the control lever to the left until the tension lever contacts the stopper. This causes the spill ring to move to the right and remain in the full load position. Next, let's see what happens at maximum engine speed. If the engine speed rises above a predetermined limit, the centrifugal force of the flyweights becomes greater than the tension of the control spring. When this occurs, the control lever and the tension lever are pushed to the right. This moves the spill ring to the left, reducing the amount of fuel injected. This prevents the engine from overrunning. Finally, let's see what happens under partial load conditions. When the accelerator pedal is depressed only halfway, control spring tension is very small. This means that the flyweights are allowed to swing outwards even by the small centrifugal force created at idling. This reduces the amount of fuel injected, and the engine speed is kept in the medium range. Now, let's review the operation of the all-speed governor under various conditions. This shows the operation of the governor when the engine is started, then at idling, then at full load, at maximum speed, and finally under a partial load. Let's repeat this one more time. Engine starting, then idling, the full load condition, the maximum speed condition, and under a partial load. This graph shows the relationship between the amount of fuel injected and engine speed. The amount of fuel injected is expressed along the vertical axis, and the engine speed is expressed along the horizontal axis. The blinking line indicates the amount of fuel injected and engine speed when the engine is started. The speed is very low, but fuel injection is at the maximum level. This is due to the additional fuel injected during starting. When the engine is idling, the engine speed is still low, and fuel injection is also kept at a low level. At full load, the accelerator pedal is fully depressed. A large amount of fuel is injected, and the engine speed keeps rising until it reaches a certain level. When the engine speed reaches this level, the amount of fuel injected begins decreasing so that the engine speed will not go too high. Various types of lines may be drawn for the partial load conditions depending on the amount the accelerator pedal is depressed. Reading from right to left, the accelerator pedal is depressed about 3/4 of the full distance, about 1/2 of the full distance, and only 1/4 of the full distance respectively. So you can see how the engine's speed is regulated according to the accelerator pedal position. This is the unique aspect of the all-speed governor. Next, let's take a look at the minimum-maximum speed governor. The minimum-maximum speed governor works in exactly the same way as the all-speed governor at starting, during idling, under full load, and maximum speed conditions. Under the partial load condition, however, even if the amount of fuel injected remains about the same, the engine speed has no ceiling and can increase continuously. In other words, the amount of fuel injected increases in exact proportion to the amount of accelerator pedal movement. For this reason, a diesel engine with a minimum-maximum speed governor gives the driver the feeling that he's driving a vehicle with a gasoline engine. The minimum-maximum speed governor is constructed in the same way as the all-speed governor, except for the design of the control spring. We have just studied the governor, which controls the amount of fuel that is injected. We will now look at the timer, which determines the fuel injection timing. The VE pump has an automatic timer. This type of timer is designed to automatically control the timing of fuel injection in accordance with the engine's speed. The timer is not visible in this cutaway model, so let's look at a cross-section of the pump cut along the broken line. This shows the construction of the automatic timer. The fuel pressure inside the pump housing varies in proportion to the engine speed. As the fuel pressure rises, it overcomes the force of the spring, pushing the timer piston to the left. This causes the slide pin to turn the roller ring clockwise, and the injection timing is advanced as a result. Since this alters the relative positions of the cam plate and the roller, it advances the timing of the reciprocating motion of the pump plunger as a whole. In other words, the injection timing advances with the increase in the engine speed. Another function of the automatic timer is to act as a load sensing timer, which controls the injection timing in accordance with the load on the engine. This timer retards the injection timing while the engine is running under a small load to minimize noise. Let's study the operation of the load sensing timer. We already studied the flyweights and the governor sleeve when we discussed the governor. When the load on the engine is large, the flyweights remain closed, and the orifice in the governor sleeve also remains closed. The pressure inside the pump housing remains the same, so the timer's advance rate also remains unchanged. As the load becomes smaller, the flyweights begin to swing outwards, and the orifice begins to open. This allows the fuel inside the pump housing to escape to the suction side of the feed pump, and the pressure inside the housing drops as a result. This causes the pressure inside the automatic timer to fall. As a result, the injection timing is slightly retarded. We hope you now understand the two functions of the automatic timer. Finally, we'll study the automatically controlled cold starting device, or ACSD. This shows the automatically controlled cold starting device when the coolant temperature is high. As the coolant temperature drops, the thermal wax shrinks, and the lever is moved to the right by the spring. The movement of the lever causes the roller ring to rotate clockwise, advancing the timing of fuel injection and increasing the idling speed. The engine's cold startability is improved as a result. We will now study some important points concerning the removal of the VE-type injection pump from the engine. We will use the VE pump for the 3L engine as an example. First, we remove these parts. If the timing belt is to be used again, you will first need to set the belt in the correct position and paint match marks on the belt and pulleys so that it can be fitted in exactly the same position later. Let's see how this is done. First, you turn the crankshaft and bring the number 1 cylinder to top dead center of the compression stroke. When you do this, you must be sure to turn the crankshaft in the normal rotational direction of the engine. Then make certain that the timing marks on the camshaft timing pulley and the pump drive pulley are aligned with the timing marks on the cylinder block. Next, paint match marks on both the timing belt and the pulleys that are driven by the timing belt. You can now remove the tension spring. Loosen the idler pulley bolt and remove the timing belt. Remove the pump next. But first, you must remove the pump drive pulley using SSTs. These parts are removed next. Now you can remove the pump. Whenever you remove the pump, you need to check the tension spring and timing belt for any sign of deterioration. To check these parts, first measure the free length of the tension spring. Then visually examine the timing belt for fraying and other damage. The pump is installed in basically the reverse order of its removal. First, install the pipes, hoses, and injection pump drive pulley. Next, attach the tension spring. Pry the bracket of the idler pulley towards the left as far as it will go, and tighten down the idler pulley bolt. Align the timing marks on the crankshaft and camshaft timing pulleys with their timing marks on the cylinder block. Then fit the timing belt, lining up the marks that you made during removal. Be careful when you fit the timing belt, as the pump drive pulley turns freely and may cause the positions of the match marks to change. If you install a new timing belt, align the timing marks of the pump drive pulley and cylinder block. Loosen the idler pulley bolt to tighten the timing belt. Then turn the crankshaft 4 full turns in the normal direction of engine rotation. And check that the timing marks on the pulleys are aligned with the timing marks on the cylinder block. And retighten the idler pulley bolt. Install all the remaining parts and reassembly is completed. The next point is the checking of the injection timing. This is done by measuring the stroke of the pump plunger with the number 1 cylinder set at top dead center of the compression stroke. To measure the stroke, you first turn the crank back until the number 1 cylinder is about 25 to 30 degrees before top dead center. This corresponds to the bottom dead center of the pump plunger. Then remove the distributive head plug bolt. Attach the plunger stroke measuring tool and a dial indicator, and set the dial indicator to 0. Then recheck to see that the dial indicator remains at 0 while slightly rotating the crankshaft. Then turn the crankshaft in the normal direction of engine rotation until the number 1 cylinder is exactly at top dead center. Now read the dial indicator. The reading indicates the stroke of the plunger. Next, compare this reading against the specified value and decide whether the injection timing is correct or not. If you need to adjust the injection timing, you can do so by loosening the pump bolts and nuts and turning the pump as necessary. When you check the injection timing of a VE pump that has an ACSD, you must first disable the function that alters the injection timing according to the coolant temperature. This is done by inserting a spacer between the cold starting lever and the thermal wax plunger. Next, start the engine, check the idling speed, and adjust it if necessary. Before you start the engine, however, you need to bleed air from the pump if it has been removed and reinstalled. Air bleeding is done by operating the priming pump of the fuel filter. To check the idling speed of the engine, warm up the engine to normal operating temperature. Then check that the adjusting lever is contacting the idle speed adjusting screw. You can now measure the engine's speed and compare the result against the specified value to decide if the idling speed is appropriate or not. The idling speed can be adjusted with the idle speed adjusting screw. We have finished discussing the important points about servicing the VE pump. Another important servicing point is the fuel filter, which must be maintained regularly. A diesel engine also uses its fuel to lubricate the precision parts inside the VE pump and the injection nozzles. For this reason, the presence of dirt or water in the fuel will have a major adverse effect on VE pump operation. The fuel filter consists of the filter section and the sedimenter section. Water is first removed from the fuel by the sedimenter, and dirt is separated from the fuel by the filter element. If the amount of water in the sedimenter increases above a certain level, the water level sensor turns on. And activates the sedimenter warning light to alert the driver. When the light goes on, the water must be drained from the sedimenter. This is done by loosening the drain plug and operating the priming pump. When the water has been completely drained out and fuel starts to come out, close the plug. Draining of the sedimenter is now complete. If the fuel filter element is clogged, you must replace the fuel filter, as it will cause the engine to malfunction. All servicing of the VE pump must be done especially carefully, with reference being made to the appropriate repair manuals. This brings us to the end of our study of the VE pump. A VE pump may look extremely complex, but its operation is governed by combinations of various simpler mechanisms. If you look at these mechanisms one by one, they are relatively easy to understand. We hope you will use this video effectively, along with the team manuals and repair manuals, to gain a better understanding of the VE-type injection pump.